So far in this unit on capacitance in chapter 24, I've been describing capacitors as an easy means of storing electrical potential energy. Well, exactly how much potential energy? Let's go through that here. Okay, so potential energy stored in a capacitor. So what happens when you charge up a capacitor with a battery? Well, you're going to have a decrease in the potential energy associated with the battery as it uses energy to do work. Let's assume that there is no heat loss in the process of charging up a capacitor. Therefore, this then leads to an increase in potential energy that is stored in the capacitor. So let's describe it with the simplest possible circuit diagram, something that just looks like this. Okay, so we've got a battery here that has a voltage V. Here's high potential, here's low potential. Okay, and then right here is a capacitor with capacitance C, like so. And then recall essentially what happens as the battery does work. Basically, electrons are pushed in this direction, such that this side of the capacitor becomes increasingly more and more negatively charged. Electrons are kind of pulled in this direction, if you will, such that this side of the capacitor becomes increasingly positively charged. Recall that the flow of electrons stops when each of the pieces of metal, here and here, each piece of metal becomes an equipotential surface. When that happens, the voltage across the capacitor is the same as the voltage across the battery. Okay, now the battery is losing energy as time goes on while it's charging up the capacitor. So the infinitesimal change in potential energy associated with the battery is equal to the infinitesimal amount of charge that flows from the battery multiplied by the voltage of the battery. This then means that as energy begins to be stored within the capacitor, the voltage across the capacitor increases. The voltage across the capacitor, however, is a function of how much charge is gathered on the capacitor. So let's write that in terms of the following expression. Charge equals capacitance times voltage. So the voltage across the capacitor is a function. It's a function of how much charge is on the capacitor at any one moment in time. This then means that the change in the potential energy of the battery, this quantity, can now be written as the change in the potential energy of the capacitor. However, the voltage across the capacitor is a function of the charge at any one moment in time. So then therefore, the infinitesimal increase in the potential energy of the capacitor is equal to dq times V, where V is Q over C. Like so. And now what we do very simply is integrate. So on the left-hand side of the expression, we're integrating over the potential energy stored in the capacitor. It starts off with no potential energy, and it ends up with a final value U. And then on the right-hand side of the expression, we're integrating over charge. The capacitor is uncharged to begin with, so then therefore it has an initial charge of 0, and then it reaches some charge that we'll refer to as capital Q. So integrate the left-hand side, and you just end up with the potential energy stored on the capacitor, U. And then on the right-hand side here, if you integrate Q over C, and we're integrating over the variable Q, you then end up with the antiderivative of 1/2 Q squared over C. Plug in the limits of integration, and you just end up with the following. Like so. So when the capacitor is fully charged up, this is then therefore the potential energy stored within. Sometimes you'll see two other formulas associated with the potential energy that's stored in the capacitor once it has been fully charged. So once the capacitor has been fully charged, then the total charge Q that is on the capacitor is equal to the capacitance multiplied by the voltage. So then therefore, if you take this expression for Q and plug it into here, you then end up with the following expression, 1/2 CV squared. So you'll see this expression here written once the capacitor has been fully charged up. If you take this expression and plug into it the capacitance C, which is Q over V, plug Q over V here into the denominator of the expression, and sometimes you'll see this expression as well. 1/2 QV, which also describes the potential energy stored within the capacitor once it's been fully charged. So then therefore we derive this expression first by setting up the integral as I've done, but then once the capacitor has been fully charged, Then alternatively, you'll sometimes see these two expressions here to describe the potential energy stored.